Hello, everyone. Welcome to the next meeting organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Pavel. I will be the moderator of this event. And today we have pleasure to host our great speaker, Dr. Saesun Kim, who is a postdoctoral fellow at Jet Propulsion Laboratory. And today he will tell us about quantum technology in space. So it looks really exciting. As you can see, this meeting is recorded. So hopefully the video will be later available on our YouTube channel. If you have any questions, you can post your questions on our chat, and then we'll ask the questions at the end during the Q&A session. But Dr. Kim, would you like to have this lecture also more interactive so that the participants could ask the questions and interrupt? Sure. Okay, so we can also try to do it. So if there are some urgent questions, we'll maybe try to interrupt. If there are more general questions, we'll try to keep them for the end. Okay, so before we start, we would like to also announce our next event. So on June 11th, there will be the talk about the dual mode quantum computer and its applications. So Dr. Jonathan Wultz will give this talk. Later in July, the algorithmic principle of quantum phase kickback, easily explained and visualized. So Professor Bettina Just will be our speaker then. Later in July, Dr. Samuel Chen will give a talk about an advanced hybrid quantum classical machine learning. And finally, at the end of July, Zeki Seskir will tell about democratization of quantum technologies. And before we start, we'd also like to thank our partners, our sponsors for supporting us. And that's all from my side. So I will now stop sharing my slides. And Dr. Kim, if you are ready, the Zoom is yours. So thank you once again for accepting our invitation. And it's our pleasure to have you here with us. Looking forward to your talk.
Thank you. Can you see the screen?
It's yours, and just tell me when you would like to just move to the next slide.
Yeah, sounds good. So hello, everyone. My name is Saesun. I'm working on the quantum sensor at NASA's Jet Propulsion Laboratory, and I'm also the Qiskit advocate at IBM Quantum. So first of all, thank you, Helen, for inviting me for this event. And also I appreciate Powell for moderating and then solving these quantum challenges that we have. And also I think we have met before, like when I was working on the quantum localization project in Korea. So it's great to see you again. So, but most importantly, thank you everyone for being here, for investing your time to join us today and solving this problem together. And it's truly honored to be here together and share this insight of what we do at the Jet Propulsion Laboratory for the quantum mission for the space. So I hope next 40 minutes for both informative and engaging. So I encourage you to raise any question during or after the talk. So not so long ago, quantum physics was just a philosophical concept that a lot of scientific communities really have a hard time accepting this philosophical weirdness, but now they accept it. Today, we stand on the threshold of the new era, where the quantum technology promise precision measurement, exponential computational power, and unbreakable encryption, which seem to be impossible just a few decades ago. Now with many promises, NASA is also investing this technology, quantum technology, which can be the key technology for the space exploration and development. And currently, such as a quantum computer, quantum communications are being conducted at the NASA. But today's talk, I will focus on the 3 quantum sensing technologies. Next slide, please. So the 3 technologies I will introduce are atomic clock, and ultra cold atom, and then the Rydberg sensor. So first, the atomic clock is very accurate clock designed to enable the communication and navigation for the deep space mission, like more than Mars or beyond. I will introduce NASA's mission of the deep space atomic clock, and how we miniaturize it and then put it into the space. And second thing is the ultra cold atom technology, which bring the temperature of the atom to close to absolute zero temperature. And NASA recently put this laboratory, cold atom laboratory, onto the International Space Station. So I will discuss why NASA is interested in this technology and how it can help for the future mission at the NASA. And lastly, I will introduce the Rydberg sensor, Rydberg technology, which measure the RF signal by utilizing the unique quantum property of the atom. Since this technology has been around slightly more than 10 years, it's still under development and there is a lot of controversy and challenges we need to solve it. But I will also talk about that. And using all this technology, I will discuss the current missions and how the quantum can help the space exploration in the future. And just want to let you know that I don't do all this work. I just joined NASA like 6 months ago, so I'm very new on this field. So I'm not representing all this technology or anything like that. I'm talking about our group's work and also other groups' work at the NASA. So I don't want to get a credit for this other work. So the next slide, please. So the quantum clock is the one of the technology that is critical for the communication in the space. So the image that you are seeing right now is the deep space atomic clock. NASA sent it in space in 2019 and completed its mission in 2021. And this clock is so precise that let's give us some kind of comparison. So your typical watch you wear normally, it have a like error of 1 second. It give you like delay of 1 second every 10 days. But with the atomic clock, like this deep space atomic clock, the error or delay is like 1 nanosecond on every 10 days. It means that this clock is billion times more accurate than typical watch people usually wear. So why do we need this accurate clock and why do we send this clock in the space? So to understand this one, we need to know that how the time is related to positioning your location. Because to position the location of the satellite, position of the spacecraft, it's really important to know the exact timing. Next slide, please. Next slide, yeah. Oh, animation is broken. So let me give you an example. I mean, the picture looks weird, but just think as there's a 2 clock right now in Washington, D.C. and LA. And the time is all messed up, but one is the LA time, which is about 10:20 right now. And then the other one is the Washington, D.C., which is a 3-hour apart. So the slide is weird, but just imagine there's a 2 different clock with a different time zone. So time difference in the LA to DC is about 3 hours. So in other words, that right now it's like about more than 10 past, and then DC will be like 1 o'clock in the afternoon. So which means that when you look at the sun, the position of the sun, since the Earth is rotating, orbiting around the sun, DC and LA, when you look at the sun's angle, it will be slightly different. For LA, we just have a sun is like just rising, and DC it's kind of passing the noon. So given that information, we looking at the angle of the sun and look at the clock, we know where we are. So for example, if I bring my clock from the LA to go to Washington, DC, my clock will tell me about it's 10 o'clock, but sun's location will be afternoon. So then we know that, there must be some kind of distance difference between my clock's location and the current location. So I know that distance between the LA to Washington by calculating the angle and then the time, what time is right now. And this is how people use the clock long time ago to navigate for really long, like distance traveling. Can you go to next slide? I'm pretty sure the animation will be broken. Okay, it's not that broken. So if like long time ago when people just sailing like far away distance because there's no GPS technology, so a lot of sailors, they use the clock and using the sun's angle to predict where they are. So let's say we bring the watch from the LA, let's say we travel to Korea, then the sun location is changing. And when you travel 4 days or 2 days, then we look at the angle and look at the clock to estimate how far away from the LA. And this is how people locate where they are. And as you can see that if the clock slowly drift and become a bad clock, then we cannot use that clock anymore, because this clock information will not tell me about the location if the time is delayed. And like for a long mission, like 1 year or 2 years, this slow delay will accumulate and we cannot use the clock anymore. So that's why over 100 years ago, people still need a good clock, but it's not really accurate to find a good location of where we are. Next, please. Okay, so fortunately, with the advance of the GPS technology, now satellites give us the exact location. So people here nowadays, we don't need to bring the clock and then angle to measure the sun. We don't need to do that anymore. Now the cell phone will calculate the exact location for us, and everything will be instantaneously. That's really nice for us. But now the clock become more important and play more critical role in this finding the location, because now for satellite is sending us information about where they are and what time they are sending that information. And then using that information, and then our phone will calculate and where we are exactly. So if there's a slightly delay on the clock on the satellite, then this will give us the uncertainty of our location. So that's why on the satellite, clock also need to be very accurate. So this is a reason why the atomic clock was first developed and then put it onto the satellite right now to pinpoint where we are. But let's say when you go to like far away distance, like more than the Mars or beyond the deep space, it will be very difficult to pinpoint where we are, because now there's no GPS satellite in the Mars or any other place beside Earth. So if you go to next slide, let's say if we are traveling to the Mars, then now it's hard to find the position. So what people do is that we send a signal from the Earth to the spacecraft, and then spacecraft will receive the signal and send the signal back to the Earth. Then using this time delay between the sending and receiving the signal, we can calculate the distance information. Because we know the speed of the light or speed of the signal, then we know the time delay between this going and coming back. We can easily calculate the distance by just multiplying the velocity times time. But for the Mars or beyond, like for example, Mars, it can take up to 40 minutes to calculate the position. So then during the 40 minutes, spacecraft can move. And also because of this take of 40 minutes, then it's very inefficient to calculate and try to optimize all the orders of the algorithm and everything, because it takes so long time to do that. So that's why there's interest to make it more accurate and faster, more efficient way to calculate the location. So one way to do it is that if you put the very accurate clock, doesn't have a drift, put it into the spacecraft. So instead of sending the signal from the Earth, send it to the spacecraft, bring it back to the Earth and calculate it, we can just put the atomic clock onto the spacecraft. Then spacecraft will calculate their location by themselves. So then they can just receive the signal and calculate the time. So this will be much faster and also very more accurate. For this reason, NASA is currently developing the atomic clock to fit it into the spacecraft. Next slide, please. So to understand the atomic clock, we need to know how the conventional clock works. So for example, if you look at the old clock, I mean, maybe if you go to your grandfather's house, you might have a big pendulum clock. So when the pendulum is swinging once, it kind of give you the 1 second. So using that, 1 swing, 1 second, 2 swing, 2 seconds. So by using the oscillation, we can track up what time is it. But when we have an electronic clock, which is a little bit better than this pendulum clock, now the electronic clock have a device that oscillates 30,000 times in a second. Some device can oscillate like 30,000 times really fast. And using this 30,000 oscillation, we can say that's a 1 second. So instead of pendulum is swing once, now we use the device that oscillates 30,000 times and we use them as a 1 second. But now if you use the cesium or different atomic species, there's an electron also kind of oscillate. And if we can use that signal, we can make it much accurate clock. For example, in the cesium atom, there's a 9 billion oscillation in a 1 second. Electrons are oscillating 9 billion times in a second. So if we can use that 9 billion oscillation as a 1 second, we can define a second much precisely, and we can have a better clock for these things. So how this atomic clock work? So principle of the operation is actually simpler than you think. For throughout the talk, I will not talk about entanglement or superposition. Of course, you can use all these things to make a clock better or all the atomic sensor better. But for the public talk, I will just make it not really mentioning anything about the entanglement or superposition here. So let's say I'm shining the light to the atomic system. When you click enter, you will see the laser. Okay. So when I shine the laser to the atomic system, then because the atom have a very unique frequency they like, I mean, atom have a favorite colors. So when they match with their favorite color, they like to absorb the light and emit the light. And we call it natural frequency or like atomic transition. When you click next again, then now there's a detector. Let's say we are using the detector to collect this light. So if we change the laser frequency, when I write it down on the x-axis here, so when I change the laser frequency, and this red line is the atomic frequency, atomic transition, or atom's favorite color. So if I change our laser color to far away from the atom's favorite color, atomic natural frequency, then this light coming out from the atom will slowly decay. So when you measure by the detector, when atom is emitting the light, when you change the laser frequency, the light coming out from the atom will slowly decrease. But when you tune our laser to exactly match with the atomic transition, light coming out from the atom will be the maximum. So if we can fix this light, like we change our laser frequency and fix at the maximum intensity, then we can fix our laser source at the atomic transition. One thing good about the atomic transition is that atom never change the property. So if you bring that atom to like United States, LA, DC, or Korea, or India, or different places, atom always have the same property. If you can isolate the electric field or magnetic field, atom always have the same property. So that's why where you are, it doesn't matter if you use the atom to like control the laser frequency, and if you can fix the laser frequency to the atomic transition, our laser will not change the frequency no matter what, and our laser frequency will be constant over millions of years. So if we can fix our laser frequency to the certain atomic transition, we can use it as a clock, because now this frequency is not changing over time, and we can use the oscillation and frequency as a 1 second. So that's why we can use this laser as a clock. So can you go to next slide? So I will talk about how the NASA is making a deep space atomic clock and sending it to the space. The atomic species that deep space atomic clock use is the mercury ion. And when you click it, you will see the 2 energy level structure. Can you click enter?
Yes.
Yeah, okay. So atom have a 2 stable orbits. So mercury ion have a 2 stable orbit. Let me code it as a 1 and 0 as just representing the 2 different orbits. And when I shine the laser light, can you click? And when I shine the light, this will interact with the stable orbit at the 1, and then atom will see this light and emit the light. And when they emit the light, all this electron will go to the orbit 0. And all the atoms go to the orbit 0, then there's no atom in the orbit 1. That's why even though we shine the light as long as, if we keep shining the light, no light will coming out, because now all the atom is in the orbit 0. So in order to make them to orbit 1 again, when you click again, so then when we send a microwave to couple these 2 transition, then all the electron will go back to the 1 and go back to the 0, and it will oscillate, go back and forth. The population will go to 1 and 0. While doing that, light will coming out, and we can measure the signal. And this signal is by the microwave, and it's about 40 gigahertz. And this is coupled to the atomic transition, so then this 40 gigahertz will never change, because it is the atomic transition. Can you click next? Then this is how the schematic works. We first capture the ions, like mercury ions, inside of the trap. And then using the microwave and then lamp, to shine the light and also shine the microwave. So then when our microwave is matching with exact transition of the atom, then light will coming out. And we can measure by the detector the maximum, and then we want to fix our microwave frequency at the maximum intensity the light is coming out. And when you do that, our microwave source will be stable and the frequency will never change, and we can use it as a clock. Next slide, please. So this is actual how does it work as experimentally, because I was just talking about the theoretically. So here, we first prepare the vacuum and then put the mercury atom inside of the vacuum. And we use electric field to ionize the electric atomic state. So ionizing means that we take the electron, take it apart from the atom. Now then that this is neutral atom become ion, which have now charge. So which means that we can control the movement by the electric field. So as you can see on the screen, there's many poles, like 16 poles and quadruple pole. So we put the rod and then apply the electric field. Then this will create the repulsive and attractive force to the atom. So then atom is slowly moving toward the center, and all the mercury ions will be trapped at the center of the chamber. Now we send the light using the lamp and also microwave to the system. This will emit the light, and then we can detect using the detector. And then using the just finding the maximum intensity and fix our microwave frequency to the maximum intensity, we can use it as a clock. Can you go to next slide? So now this is the how atomic clock overall looks like, and this is a spec of it. So it weighs about 17 kilogram, which is about 40 pounds. It's about the size of the small rice cooker. And it uses about 44 watts, which means that for 1 hour of using the electric rice cooker, atomic clock or quantum clock can run for 20 hours. And this technology was sent into the space in 2019 and completed its mission in 2021, and shows a very great result of this. And originally, it was going to put it into the Venus mission for 2028 for the follow-up mission, but unfortunately, it was canceled. But recent study shows the very interesting suggestion of the atomic clock for the finding a dark matter, try to figure out the mystery of the universe. Dark matter is something that nobody really knows. Physicists call it dark matter because it's kind of dark. We have no idea what they are. So people believe that there's a lot of dark matter around the sun because sun have a stronger gravity. So if we can bring this atomic clock to the near the sun, then because of the dark matter we interact with the atomic clock, you will see some kind of change of the atomic clock. So that's why people believe that we can measure the dark matter search using the atomic clock. So there are a lot of interesting proposals coming up. So hopefully I wish to see the atomic clock back again to the space mission soon. So next slide. So now moving forward from the atomic clock, I would like to turn the attention to another groundbreaking technology. But before we do that, I'm happy to answer any question. If you have any question, I can just move on to.
Let's see on our chat. There are some questions about the slides, whether they will be shared. So we'll see. So of course we can consider it. I don't see any merit questions now, but maybe someone would like to unmute. Oh, there is a question from Aubrey. Does the technology for the clock use ion traps?
Yes. Actually, they are using the ion trap. So the reason why we make our mercury ion is through using the ion trap technology. So we can trap them into the center. And actually, I didn't mention that the good thing about this is there's no vacuum pump. Usually, you need to put the vacuum pump for the ion trap and all this system. No vacuum pump and no laser, and everything is not cooled down. It's just kind of just stay there. So it's really good. But we are actually leveraging the ion trap technology.
Great, thank you. Do we have more questions? Maybe someone would like to unmute and ask. Yes, there is a request to explain dark matter clock.
That's kind of beyond my pay grade, so I cannot really say anything about it because I don't really know
That's
about it.
fine.
It's there's a proposal about the atomic clock to measure this dark matter, but as many people know that we don't really know what dark matter is. So there's many models about the dark matter, and what we do is just using the technique to measure this domain and say, oh, this model is wrong, and just measure this domain and this model is wrong. So we kind of reject the model to figure out which dark matter model is proper model. So we don't really know yet about dark matter, and I don't really know in the dark matter. So I'm not the expert to talk about the dark matter. Sorry.
Okay, that's fine. Fair enough. There's another question from Ron. How sensitive does the photon detector need to be in the clock feedback?
I think that's a good question, but I think for this application, it's not really critical because we are just measuring the intensity. So, I mean, again, I just joined this group for 6 months, actually 8 months, so I don't really know very much about everything. But my just suspicion is that the detector efficiency is definitely important, but we are not really leveraging any quantum light or anything like that. So other things are more affecting the system more than the detector.
Mm-hmm.
So for example, like the ion have to be captured and all this noise can be generated from the just trapping or vacuum or many other things. So I believe that there will be more problem, but I don't really know. Sorry.
Okay, that's fine. Thank you. Do we have more questions?
We can come back after the talk if people
Yes,
can have
yes,
a more
yeah.
question.
Yeah, let's go on.
Okay, so now I'm going to introduce the cold atom technology. In 2018, NASA put the laboratory on the International Space Station that could control the state of the atom and lower the temperature, like very low temperature, bring them close to the absolute 0 Kelvin. It's actually 1 picokelvin, which is 100 billionth of the 1 Kelvin. And NASA opened up the laboratory to the public, so the scientists around the world can register the time and study this cold atom research in the ISS. So until recently, a lot of experiment has been conducted and interesting studies have been published. So next slide, I will talk about how this ultra cold atom technology started and how it became a space mission and why NASA is interested in this technology. So generally speaking, when we're thinking about the state of matter, we can think of the three different states: solid, liquid, and gas. So in a high temperature, atoms are moving randomly in the gas state. They are moving quite fast. And if you lower the temperature, the movement of the atom will be gradually decreased and become a liquid. And if you lower the temperature further, atom will become a solid and almost lose their movement or momentum. So in thermodynamically, movement or how random they are moving is related to the temperature. So if we can control the movement, we can lower the temperature. Can you go to next?
Mm-hmm.
Okay. So then if you lower the temperature further down and get closer to absolute zero, atom will change into the new state of matter. Can you click it? So if you lower the near absolute zero, can you click again? So if your movement will slowly decrease and they are all kind of freezed. So then each of the property of the atom disappear and it become a new state, act very differently. This state is called Bose-Einstein Condensate, short in the known as a BEC. So for better understanding of this, let me give some kind of example. Not example, but kind of analogy. So in the quantum mechanics, object like a particle exists in a wave state, so like an oscillation. So some atoms have a fast oscillation and some atoms have a slow oscillation, and they are moving very differently. So if you've been to any orchestra or symphony, like any violin performance, you can understand it this easily. Before the performance begins, instruments are preparing to play different notes and they're just making different sounds. With so many like instrument playing different sound, but because they are playing different note, you can see which instrument is making a noise. You can see that the violin is making a sound A or that cello is making a sound B. So you can kind of figure out that which instrument is playing which sound. But when they start the performance, when they just tune their system, so then everybody playing the same note, then it start to making a whole one note together. Whole symphony is making one note. So we don't really know that who is playing what note, because everybody playing the same note. They're all in same tune with the harmony. So that's why I don't really know that violin is making a note or that cello is making a note. Everybody making a same note with the same sound. Similarly, if we lower the temperature of the atom, and then all the atoms' oscillations are kind of into the same oscillation, they all the property of the each particle disappear, and we cannot really pinpoint which particle is which. It acts like a one giant orchestra with the harmony, like a giant atom. And so like millions of atoms act like a one giant atom and one oscillation. So when Bose and Einstein first come up with this idea, they really didn't think that it's possible, because to make this kind of state, you need to cool it down and then cool it down really, really low temperature such that it should be the coldest place in the universe. So when 1925, when they proposed about this idea, they don't even think that it's even possible. And it takes about 70 years to achieve it and make the BC in the experiment in the lab. And to make this BC for 70 years, there's a 6 Nobel Prize coming out to make this work. Of course, laser technology, ion trapping, and transistor for electronics and cooling, and also BC technology, BC itself. So many scientists now, we can make a BC in the lab. So now we can explore this new state of matter, and then we can test with the quantum world with using our laboratory, in the laboratory. And ironically, the most important technology to lower the temperature is laser. It might be a little bit strange to think that we need a laser to cool the temperature, because laser usually used to heat up the system. So let me explain the laser cooling. Can you go to next slide?
Sure.
So as I mentioned in the previous slide, when the like atomic clock, when you shine the light, it will absorb the light and emit the light. And during the process, atom actually slow down or change the momentum, because when you send the light, the photon, the light particle have a momentum, so it will collide with the atomic system, and atom will change the momentum. So when atom is going to the one direction and we send the light to the other direction, then atom will lose the momentum amount from the light and then slow down. So when you click again, atom move to one direction, and then light coming out to the other direction, it will absorb, emit the light, and slow down. So if we can prepare the laser into the XYZ direction, when you click one more time, so then XYZ direction, then we can capture the atom into the center of the laser and then slow the atom down. So like millions of atoms, when you shine this laser light, then atom is slowly merging into the center of the laser and slowly cooling down, because we are using the laser to slow the atomic movement and slowly cooling down the system, because movement or momentum is related to the temperature. On the next slide. So now when you put this atomic system into the small chip, like we use the laser to bring close to the atomic chip. Can you click on one more time? Then we can, this atomic chip is producing the magnetic field. And just like a magnet, N pole is attractive to the S pole, atom will be attracted to this atomic chip. And what happens if you flip the magnet is that it will be repulsive. So same thing happened, that if we can flip the atomic state, then atom will be repulsive from the atomic chip and go really far away. So what we can do is only flip the atom when atom have a fast movement, or actually in the hotter state. So we can do that with the radio frequency. We can apply the radio frequency to flip the atom to the different magnet. We can just push it away. It sounds very difficult, but you guys doing it every day in your life. So when you drink the coffee, when it's too hot, you blow the surface of the coffee because it's too hot. What you do is actually blowing the hot particles away from the coffee cup, so then coffee will cool it down slowly. Similarly, we are doing the atom, we put all the atom into the one small cup, and then blowing the hot particles away using the radio frequency. So then atomic state will slowly cool it down. And actually this cool it down, we can create the BC state. And this is called evaporation cooling technique. So now physicists can use this one to create the BC state. And now we can access of the new quantum state. So a lot of physicists are very excited about this state and they want to study new phenomena of the quantum mechanics. So many universities and many institutes or laboratories begin to study these new conditions and actually create a lot of understanding of the quantum mechanics. But there's one big problem for the physicist because it's gravity. So when you click it, can you click it? When you shut off the laser, when you not using the laser, it will slowly drop because it's in the side of the vacuum. So when we turn off the laser, atom will slowly fall down due to the gravity. And because it's a vacuum, people already know that it will just accelerate even though it's how light it is. So atom will just fall down, free fall onto the vacuum. In the laboratory, we are using very small system. So that's why we can only study this system like less than 0.1 second because it will start drop and we cannot really measure it because it drop right away. So if you can conduct the experiment, let's say 5-meter tower, we can just do barely 1 second of experiment. So we want to study longer time and what's going to happen, how it changes, but we have a physical limitation that we cannot really do it further. Can you go to next slide? So this is the jet propulsion laboratory's BC system. So you can see on the screen that very tiny glass cell. This is where the BC is created, which means that in this system, we can only study for 0.1 second because gravity will attract the atom to the ground and we can only have access them for 0.1 second. So the question will be then, how can we do this experiment more than 0.1 second? Let's think about it for a few seconds. How can you do the experiment that is not affected by the gravity for a long time? Like how can you create the zero gravity? So many physicists thought about it and how to get rid of this effect of the gravity, and they found a very elegant solution. So what if we just put all the lab and just drop it to the ground? So if we can put all this vacuum pump and all this computer, electronics, all this multi-million-dollar experiment, put them into the box and simply just drop it. Can you click the slide? So when you can put that all into the box and then just drop it, click again. Then before the box break and hit the ground, at least we will have no gravity before it break out. So physicists eventually start building this multi-million-dollar mini laboratory and put it into the box and start dropping it. It sounds like a mad scientist, but they actually really did. Can you go to next? So first experiment was dropping in the 120-meter tower. It's about 100 feet taller than the Statue of Liberty. This means that during the free fall, this experiment have a 5 second of zero gravity, and it will hit the ground after 5 seconds. And they dropped a $1 million experiment from the 300 feet away, and then physicists successfully experienced the zero gravity, and BC was studied in this zero gravity. Eventually, they are not really satisfied about this result. They want to try even further. Can you click one more time? And in 2018, the laboratory went up to the sky by the rocket and published in the Nature paper that first space-borne BC. And now, because they used the rocket to launch it to the space, so then this BC was created in the space and falling down about 200 kilometers. And during this time, about 6 minutes of drop, people study many different interesting things about the BC and how they react under zero gravity. So they were able to extend the time of the BC. So now we are sending like millions of dollar experiment to the sky to slow down this insanity. So NASA declared a mission to put the lab onto the space station to calm down all the physicists. Because in the space station, there's very little gravity. So we can do the experiment almost near gravity. So which means that we create the system and we can have it for a really long time without falling down to the ground. So this mission is called Cold Atom Laboratory. And can you go to next slide? And this is the equipment that was put into the space. They used the rubidium species, so they put the atom into BC state. When you look at the A, this is a place where the atomic state is prepared. So put the atom together with a small vacuum chamber. As you can see, there's a little chip. You cannot really see that, but in the top of it, there's a small chip on there. And then when you look at the B, this is where you use the laser signal and detector and supplying the electric signals. And then when you look at C, it's how we all combine that together with the camera and holding all these things together. Go to next slide. And this is the whole system is on the ISS. On the right side, the small box is what I talk about ABC. On the left side, the big box is where we store the computers and lasers and every control electronics, because we need to receive the signal from the ground to the test experiment. That's why there's all the devices in this big box. So thanks NASA for putting the bees in the space in 2018. There's no need to throw the laboratory into the sky anymore. Now, any scientist in the world can apply to NASA, ask for the time to do the experiment, do the interesting experiment, the BC and the zero gravity. So now the experiment only been able to do 0.1 second on the ground. Now in zero gravity, people can test up to 10 seconds. When you go to next slide. So in fact, NASA is not just scientifically interested about this technology. So I've been talking about the physicists are excited about this technology and they can study about the zero gravity, but actually there are a lot of practical application for this cold atom technology. And one of the application is measuring the gravity. Can you click it? So when you shut it up the laser, atom will slowly drop due to the gravity. And one thing is that only by the gravity. Since they are in the vacuum, there's no other effect. It will drop by the gravity. So if we can measure the speed of the atom and how fast the atom is accelerating due to the gravity, we can measure the gravity. Can you click again? On the right screen, this is how we measure the gravity using this atomic sensor. So let me look at in the bottom. So in the bottom, this is where the atom is stored. It's hard to see, but I don't have access. But in the bottom, there is something looks like a cross. And this is laser to trap the atom. And then atom will slowly merge into the center of this cross-looking black thing. And on the top, it's blocked by the metal, but actually it's same thing is up there as well. So there's a two atomic cloud. Atomic system is cold atom is on there and then the bottom. And when you turn up the laser, it will drop it together. So on the bottom, atom will drop. On the top, but atom will also drop together. But there's a 1 meter difference between the top atom and bottom atom. So when the gravity is pulling this atom, because gravity is different in the different location, even though it's only 1 meter away, atom feel the difference of the gravity. So then when atom is falling down, the bottom atom will get faster compared to the top atom because it's 1 meter apart. So then top atom feel less gravity compared to the bottom gravity. So we can actually calculate the gravity difference between the 1 meter. And actually this experiment shows that even with the small object, like 30 kilogram, maybe like elementary student size, we can actually detect the human mass. So if the human enter the room, because human have a mass, human will create the gravity, this detector can capture this gravity change from the human. So why even care about this sensitive gravity measuring device? But actually, this is a very interesting device, and actually NASA is very interested about the measuring the gravity. Can you go to next slide? NASA was already interested in this measuring gravity in 2002. So they put a device called GRACE into space. So these two satellites travel around about 2 kilometers apart together and then travel around the Earth together. So these two satellites is moving together around the Earth. let's say we are getting closer to like Mountain Everest, which have a more mass. So the more mass means more attraction force. Then the first satellite will get attracted by the Mountain Everest, change the location slightly. Then by calculating the location between these two satellites, because this is moved slightly, when we measure the distance between the satellite, we will find that, oh, there's a distance is changed, then there's a more gravity. Then we can actually use this distance to estimate what's happening on the ground. So we can measure the ground from the satellite. So we can measure the ground gravity from the satellite. So which means that there's a lot of application for this technology, such as global warming. If the water level goes up, which means that ocean have a more water, means more gravity. So then there will be more gravity measured by the satellite. Then we can tell that sea level is increasing. Also, let's say in the iceberg or in the like glaciers, the water is melting inside of the glaciers, then we cannot really tell by the picture, because picture only tell the just how they looks like, but they don't really tell what's inside. But when they melt inside of the glaciers, and there's a change of the mass, which means that we can find the change of the gravity. We can measure the gravity change to estimate what's happening inside of inside of the glaciers. So if we can use the quantum sensor to the satellite and then measure the gravity around the Earth, we can actually then detect those kind of changes. A lot of recent study already shows a lot of great work from the Europe that they use the gravity sensor to measure the underground tunnel and like mapping the sea map, and also even try to measure the gravitational wave from the space. So if we can put one satellite, just one atomic sensor, put it onto the space and measure this one, then we can measure more information about the gravity of the Earth. And this will help us the mission to locate the groundwater in the California, or like tracking the global warming and other weather mission as well. And another example will be accelerometer, because the gravity change means that how fast the atom is moving by the gravity. But in the space mission, when we don't have a good, like a strong gravity, let's say deep space mission, then there's no gravity. Only thing that affects the atomic system is acceleration. So if the spacecraft is accelerating, then atom will feel this acceleration. They can track it down exact velocity change of the spacecraft. Then this can be used as a sensor, inertial sensor for the spacecraft to track the position of the spacecraft. Then actually this can help the navigation in the space, which can help for the deep space mission in the future. So that's why using this quantum property, NASA can prepare for the deep space mission and navigation, and also help for the climate change and all these other mission on the Earth. Can you go to next slide? So yeah, this is another stopping point. Happy to answer any question.
All right, thank you. So actually we have some questions. So here I will just ask the technical questions. There was a question on YouTube. The process to rad hardening and make fault-tolerant devices in space is the same for classical bits and qubits?
I think, can you repeat the question again? I think it seems
Yes.
like very
So
quantum computing question.
yes. Is the process to rad hardening and make fault-tolerant devices in space, for instance, outer atomic clocks, is the same for classical bits and qubits?
But one of the fundamental difference between the sensor and computer is that computer, we try to really make it fault tolerant. We don't want to expose the environment at all. But on the other hand, these quantum sensors, they try to expose to the environment. So then we actually can measure something. So computer, we don't want to measure anything. We don't want to leak anything. So we make it everything secure, isolate everything. But sensors actually is slightly different. So I'm not sure that we can actually say anything like fault tolerant quantum sensor or anything like that.
Okay, thanks. I hope that it answers the question. There's another question from Ron. So he said that it's a space question. Is laser cooling also called sympathetic cooling?
Oh, pardon me?
Is laser cooling also called sympathetic cooling?
Oh, I think I know what you're talking about, but there's many different cooling technology, and for many different reasons, people use the different cooling technique. So I don't really know, but there is a way to cool the atomic system differently. So I think it's the same thing, but I cannot really tell.
Okay,
Sorry.
good, thanks. Then there is a question from Barry. When they drop $1 million experiment, do they let it crash on the bottom, or do they have a way of slowing it down to recover it before it crashes?
Yeah, I just said in kind of try to amuse the presentation, but actually they capture it so they can save it. So of course they need to realign everything. Maybe some device might be broken, but still they were able to reuse all these things together. So actually for the tower experiment, it's like they drop it, but they capture it at the bottom. So they slow down and capture it. So they have a microgravity for a few seconds and they will capture it at the bottom. And for the rocket experiment, I think they will use the parachute and just slow down and drop it to the ground. I'm pretty sure they break some devices, but it's not really crushing to the ground.
Okay, good. There is also a question from Dev. What is the experiment findings of effects of gravity on BEC at ISS?
So yet we don't have any groundbreaking yet, but I hope to have it soon. So a lot of interesting questions around there because let's say we don't really know about the between the quantum and gravity. Like I think Einstein tried to combine these two together, but we couldn't really combine these two systems together. So there's a lot of interest to see that how this quantum system affected by the gravity. So are they have a different like affecting like in the very zero gravity system, only thing affecting is no gravity, but atom also have a gravity toward each other, but something like that. I think they try to study how the gravity affect inside of the quantum system. Also, they want to see like universality, like how this transition happening for the atomic state. So there's some fundamental question they want to answer, but not yet. I think we haven't really have any great groundbreaking result yet. But actually, when you look at some of the interesting paper, they made a quantum bubble. So they use in the space, they can make a bubble BC state. So you can actually check it out. They make a cool quantum bubble.
Okay, great. There is, I guess, a follow-up comment from Ron regarding the previous question. You could use a mechanical dashpot to decelerate a dropped object. And then there is quite a long question from Stuart. So maybe I'll just read the last part of the question. What are your proposed next steps for quantum space testing? But Stuart, maybe you can also unmute yourself and maybe say exactly what you wanted to express.
Appreciate the opportunity. Sorry, it took me 15 minutes to get on this Zoom call. We're planning on proposing a quantum event up here in Canada as it relates to some of the technology that is being developed by some of our Canadian scientists in quantum radar. So I was curious in terms of your proposed next steps for quantum space testing. You've gone from terrestrial based to low Earth orbit testing. What's the next step? I think there may be some synergies with what you're doing in the United States and what we're trying to do up here in Canada.
Which technology are you talking about? Like atomic clock or gravity matter or
No, we're
radar?
talking about quantum radar.
Actually, next slide is quantum radar. So maybe
Oh,
after
wonderful.
the slide, we can talk about it. Yeah.
Okay.
All right. And
so maybe we can move forward the next slide and then.
Sure.
Yeah.
Let's move on.
So, oh no, go to the previous slide.
Oh, okay.
Okay. Yeah. So here. So last technology I'm going to talk about and introduce is Rydberg sensor. And this technology has been recently selected as an innovative technology concept by NASA, and it's currently being developed right now. And actually, it's by one of the colleague, Damin, who is in the different group. So actually, I'm keep telling you again that all this technology is just by not by our group. It's like kind of shared work between the different group at the JPL. So this leverages the particular state of the atom, which is measure the wide frequency bandwidth from kilohertz to terahertz. So when I was in Oklahoma as a PhD student, one of the faculty member, Dr. Schaefer, was first demonstrate this technology. So it's very exciting for me to see that NASA is developing this technology as well. So why NASA is interested in this technology? Can you go to next slide? So in the NASA's communication or remote sensing application, satellite uses many different frequencies to measure the these missions, like using for the different radar to measure the different weather system. So for example, it used the VHF band to study the tomography of the Earth's surface, UHF band to study the snow and rain accumulation, L2S band to study the glaciers, and CXKU band to snow and rain precipitation. And so in order to do all this kind of research into the one satellite, you might need 6 different radars to cover all these things together. But if you can use one atomic sensors, actually, can you click it? So you will need a 6 satellite. Can you keep click it? I think there's 6 satellites. And then when you click one more time, then if you can do it with just one single atom, not one single atom, what I'm saying is one just atomic sensor to cover all this kind of measurement, then it will be more efficient and more economical for the space mission. So to use this as an atomic radar or Rydberg sensor, we need to understand the principle of the Rydberg technology. Can you go to next slide? So to use the atom to capture this all the frequency at once, atom must be very sensitive for the environment. To do that, specifically, like we need a specific state of quantum state called Rydberg state. This state is very sensitive for any kind of environmental change. But to do that, let's give the animation is a little bit broken, but let's click next one. So we can actually use the laser to control the orbit, and we can make it really, really large atom. When you click one more time, then we can actually use the atom, like, let's say, for example, in the hydrogen, we can put the hydrogen orbit 1 to orbit like 130 or something like that. In that case, we can increase the size of the atom, which is close to 1 micrometer. So this means that it's size of the bacteria. So then one single atom is size of the bacteria. So it's very, very giant atom. Since it's a very huge atom, if there's a small electrical signal around it, electrons react very sensitively and affect the orbit, then we can measure the change and use it as a radar. Can you go to next slide? So this atom can be either rubidium or cesium. Either case, we can use the 2 lasers to put it onto the very high orbit, so make it really big giant atom. When you click it, so then let's say we can use rubidium to put it into the 48th orbit. Can you click one more time? Now they are in the very high state. They are very sensitive for any kind of environment. When you click again, if you send like radio frequency or some kind of different external field, this will be affected and we will see some kind of change. Can you click one more time? So this is one of the things that NIST did. That on the x-axis, you can think as the laser frequency. So like an atomic clock or cold atom system, when we change the laser frequency from the center to go far away, then the light coming out from the system will decrease. Of course, this is slightly different. I'm just simplifying it, but you can see on the black traces, the maximum intensity will slowly decrease when you tune our frequency. So when there is an external field applied to this system, this peak will slowly split amount of the electric field applied to the system. So then we can use it as like a radar. When you click one more time, and actually people demonstrate like fun experiment with the guitar. They kind of use it as like AM radio, so amplitude modulated radio. So they put the guitar signal and put it into the carrier, and then they just modulate the sound and make a noise into the speaker. And using the atomic system to measure this kind of electrical signal and modulated sound and save the file onto the computer. Of course, it's fun experiment, nothing really about like scientific improvement, but this is very interesting demonstration to show that we can use it as a AM radio signal. So the next slide. So this is actual Rydberg sensor being developed into the NIST, National Institute of Science and Technology. As you can see, you can put the atomic system as a vapor and very small glass cell and shine the laser, and we can use it as a radio. We don't need a big antenna anymore. Very small cell can measure the signal from the different signal. So now there's a possibility to replace the 6 different radars using the small sensors with a high sensitivity. It can provide a new paradigm for the science and remote sensing, especially because it's small and convenient. I believe that this can help a lot for the space communication too. But as I mentioned that this is only like slightly more than 10 years technology, there's a lot of controversy on this technology because it's totally new way to measure the signal. Usually we use the electronic to measure it, but now we are using the optically measuring the signal. So there's a lot of things that since it can cover wide band, what does it mean? Can we really compare the sensitivity directly? So there's a lot of question about it, and also there's a lot of skeptical thoughts from the other like sciences. And also like it can cover long bandwidth, but still we need to figure out how to access all these different bandwidth. That's the open question. So there's a lot of interest and they can innovate current technology. However, there's still a lot of challenges to overcome. The next slide. But I would like to conclude my talk with the famous quote by Niels Bohr, where one of the founder of the quantum physics. So how wonderful we encounter this difficult problem because now we have a hope to make a progress. At the JPL at NASA, where we work, it's trying to develop the quantum technology such as a radar, gravity sensor, atomic clock, and cold atom laboratory to expand our human understanding and boundary of the knowledge by answering the fundamental question in physics, and also advance the technology to making a groundbreaking and new technology which once was impossible. And this development will not only help the space exploration or scientific research, but I believe that this will also transform the industry and improve our daily life of the human. So currently, physics have many unsolved problems and mystery, and also NASA is asking questions such as, are we alone or can we settle in the moon? These all the question and technical challenges give us hope because by solving these challenges, we are making progress and getting closer to the truth. So I'm very excited and delighted to be with you together with this joyful event. Thank you.
Great. Thank you. Thank you, Dr. Kim. Thank you very much for this great presentation. And now we have also time for more questions. Let's see if there are some questions on our chat. So there are some questions about the slides, but we'll later figure it out.
Yeah, I have a question.
Yes, please go on.
About the cold atoms. In the University of Toronto, there is a specialist looking at cold atoms, having a lab and students and everything. And from time to time, I listen to them. But I wonder what progress in cold atoms you are expecting to improve this technology and capacity.
So currently, our next things that we are looking for is putting this onto the space. We already put the cold atom laboratory into the ISS, but if we can put this gravimeter onto the satellite and then orbiting around the sun, oh, not sun, I'm sorry, orbiting around the Earth, then we can actually measure this gravity change. So actually, we want to have a tech demonstration of gravity sensor onto the orbit. I think that's our next step. But to do that, we need to miniaturize it. We need to make a less power consumption, and we need to make sure to improve the sensitivity, which means that more number of the atoms and much better control of the laser system and a lot of things together. So there's many room to improve to make this mission successful.
Okay, one more naive question, and don't feel bad about it. You talk about lasers, and at the time when I studied lasers, they were also talking about masers, and why masers are not used. Are they useful at all in this business or not?
I don't really, I mean, I'm not in the major area, so I never used the major, so I don't really know why we move forward from the laser to laser. I guess just my naive guess is maybe it's easier to use laser because we need to access many different frequencies, and I have really no idea. Sorry. I'm too
All right.
young to answer that question. Sorry.
It's nice to be
Okay.
young. Enjoy it. Thank you for your talk.
Thank you.
Great.
Very good talk. Thank you.
Great. Thank you. Thanks for the question. Yeah, there was also a comment from Barry, what the maser is. And there's a question on our chat: on basis of sensitivity or other features, as per your experience, how you position each type of sensor?
Oh, can you repeat the
Yes.
question again?
Yes, you can also read it on the chat.
Oh,
That's the last question. On the basis of sensitivity or other features, as per your experience, how do you position each type of sensor?
what do you mean by how I position each type of sensor? Sorry, actually.
I believe that probably he wants to know which sensors are better in terms of sensitivity or maybe some other features. So how do compare them? But that's just my guess. Maybe Anu could also
Okay.
unmute and clarify.
Yeah, Pavel, you're correct. In terms of the sensitivity, in terms of the performance and their usage, the practical use cases, where you see like which one is actually is much more preferred
Oh,
as compared to the other one.
so I since they are for the totally different missions, so I cannot directly compare them, which is better or more positioned. But I can talk about like how mature the technologies are. So atomic clocks are very mature. So they are, I think, already in the commercial level, people using it a lot. For the gravity and cold atom technology, it is still mature, but you need a still more development. Especially, I'm working on the like making a compact, less electrical power, and it's easy to use. So something like that still need to be matured. For the Rydberg sensors, there's a lot of work on it, but I think that will be the youngest one too. So in terms of maturity, but they also maybe some other people might say differently because cold atom might not be old enough, but I think it's already demonstrated to be in the space. So in the maturity, I would say that cold atom, like clock, cold atom, and the Rydberg sensor.
All right.
And sorry, there's a follow-up question. Then where you place the nitrogen vacancy NV center type sensors?
So it's hard for me to answer any like comparison because I don't study natural vacancy, and I know they are really amazing and they are quite good sensors right now. And there's a companies coming out to just using that as a sensor. But I never really researched on which is how much developed in the technology readiness level. So I cannot really answer that question. I'm sorry.
Okay. Anu, is it fine, or maybe would you like to
Oh, thanks. Thanks
clarify?
for the response. Thank you.
Okay, good. All right. So I see that there is a follow-up discussion regarding this maser. So there was a comment from Victor. Yeah, that's good. Thanks, Victor. Do we have more questions to Dr. Kim?
Yeah, there is a question. And at the beginning of your talk, you spoke about GPS, and somehow you said we can do it in space. So regardless of, so the question would be for Earth usage of GPS that we are all using daily and enjoying. The question is if quantum approach can make it even better here. I'm not talking space.
Oh, that's a good question, and actually they are doing right now. So in the ground, I think they are following the NIST standard of the like NIST has an atomic clock, and they are using that very, very precise clock to synchronize all the time, like what we are using. Like I heard that some people using for like financial trading or something like that. But yes, they are actually doing it. And what I actually discuss atomic clock is not like there is how to say this is quantum clock because we are using the atomic state, but people don't really call it as a quantum clock because we are not really using the superposition or entanglement on this case for the atomic clock. And people are actually using this quantum effect like entanglement and superposition to make much accurate clock. So there's another level of experiment, next generation experiment, the atomic clock, which they make it like even much more precise than what we have right now. So those clock, and now your good question is that yes, they are using the atomic clock and quantum clock to give us good timing on the Earth, but do we really need that good timing? Because now in the certain level, we might not get benefit for having much more accurate clock. I mean, because it's already accurate enough, do we need to make it better? So that's a different question, that do we really need it in the Earth? People say that we can measure dark matter for scientific reasons. Beyond the scientific reason, do we really need that accurate clock? I still want to know. I mean, maybe there is that I don't know, but yeah, that's still open and good questions.
Wonderful. One more not so good question.
It's a great question.
And this is, if cold atoms are limited and have a lot of restrictions in terms of position, in terms of situations like temperature and so on, maybe electronic clocks will be easier.
But electronic clock, so it will be easier and this will be fine, but atomic clock is rely on the atomic state, which is really precise. That's why we are using the atomic clock. Electronic clock, I'm not sure how much we can make it better. Maybe different innovation is happening on the different science. Maybe it might be better, but I think by far I know that they cannot really even compete with atomic clock because of the sensitivity.
Okay, great, thanks.
All right. There's another question from Aubrey, and I see that Ron has raised his hand. So maybe I'll first read the question. What was the name of the atomic clock mission?
Oh, it's a deep space atomic clock, so DSAC.
DSAC.
And you
Okay,
can see
great.
on here, you can see that that's a advertisement for the DSAC.
Great, thank you. So Ron, please go ahead.
Yes, relative to the clock stuff that you were working on for the GPS system, do you envision that at some point in the future, given that people want to travel to Mars, like you were saying, that they deploy a set of satellites that are in orbit around the sun, maybe in the same orbit as Earth? And if that is something, does that present additional challenges for keeping clocks that are that far away from each other in sync?
Oh, for the synchronizing the clock, I think that is also very critical. I heard that like a lot of people are interested in the synchronization of the clocks. I mean, as I mentioned, I keep repeating myself, just make sure that I'm not representing NASA or anything direction, anything like that. I just work here for 8 months. So just make sure that you guys are aware that I'm not representing this. But there are a lot of interest in synchronizing the clock. And I think the atomic clock can really help this one because, for example, if two satellites is communicating each other, like by the light or by some kind of signal, and try to synchronize two clocks together, if there's a drift and slowly changing the time, then let's say when we are traveling, there's some kind of obstacle like sun or different planet is blocking these two paths, then we will have a maybe day or 2 days of not communicating each other, then they will slowly unsynchronize and have a delay. But atomic clock will have no delay. I mean, they will delay, but it's very slow. So maybe nanosecond or picosecond of delay for every 10 days. So then we can actually very synchronized, even though without communicating to each other. So I believe that atomic clock will be the way to solve this kind of problem of the synchronizing issue. So, but I'm not sure I answered your question.
Yeah, I think you did. So again, what I'm asking about is,
just like we have a set of satellites in orbit around Earth where we very much know what their orbits are like, and we know how far apart they are, and that you have timing issues. If you had a set of satellites that were in orbit about the sun, such that they would be GPS for our solar system, now you get satellites that could be 200 million miles apart, and they have, everything relies on the clocks being synced. So is there any additional things you have to deal with, given that would take in some cases 16, 20 minutes to just exchange clock variances or something?
So I think that is I think the idea of the one-way communication that people want to do. I don't really know this topic very well, but just kind of my mere understanding is that I think in later we can put the clock into the, like as you just mentioned, the different orbits, and like in the sun or different moon, or many clocks in the different locations. Then this can act as a GPS satellite for spacecraft. So they can just send a signal to the spacecraft, and spacecraft also have a clock inside, and they can use all this information to navigate by themselves. So I think that is the future. Yeah, but I don't really know very much about beyond this this one.
Okay, thanks. But it sounded like you think that some people are thinking about that at this point.
Yeah, I think you can search for like one-way communication, one-way navigation, then might help you to understand better. Like that kind of keyword will help you.
Very good, thank you.
Thanks.
Great, thank you. Thanks, Ron, and thanks, Dr. Kim, for the answer. Do we have more questions?
Yes.
Yes,
There is
Itamar?
a very wild speculation that although we are so deeply delved with quantum computing and quantum and so on, people also were toying with bacteria computing.
Mhm.
That could be that the bacteria is so accurate, better than the atoms in terms of clocks, because they are very organized. They have the harmony built in, and the sync and so on.
Okay. So what is the question?
If I want a better clock for some reason, or just to make a progress or to do science, I can think about bacteria clock.
Okay. I think I never really study or understand the bacteria physics or chemistry, so I cannot really answer this question. Sorry.
Yeah, very speculative. Thank you.
Okay. Great, thanks, Itamar, for the question.
Science is also fun, you know.
Okay, there's another question from Kevin. Are there any other quantum technologies being implemented with atomic clocks, such as annealing used in CQ?
What is CQ? I'm sorry.
Kevin, maybe you can also unmute yourself and clarify.
Yeah, so this was an article earlier last year. It stands for Space Entanglement and Annealing Quantum Experiment, and it's basically communications up in space.
Okay.
NASA.
Again, I just joined here 8 months ago, so I'm not catching up all the work in NASA right now. And actually, NASA have a 10 different branches, so I'm not really sure. I'm sorry. But it sounds like an interesting question, but I cannot really answer at this moment.
Okay. Thanks, Kevin. Anyway, do we have more questions to Dr. Kim? I don't see more questions on our chat. There are some comments. All right.
We can come back to start right? Right? I don't know how to pronounce it.
Stuart Wright. Yeah.
Stuart.
Wright. Yes. does it answer all the question that you had, or
It
you
did.
can talk
I
about it
reached
more?
out to you on LinkedIn.
Okay.
My question is how, I know much of this is currently theoretical and we're still in experimental
Yeah.
phase. I'm curious how close, what kind of time frame for production of a quantum radar? Are we
So
looking at like a 3 to 5 year outreach?
it's very good and interesting question because no matter, I mean, if it's like depend on the who you ask, right? Like
Well,
same thing as a quantum.
I asked the Admiralty 3 weeks ago when I had lunch with them, and they had no idea what I was talking about. I'm meeting in Ottawa to talk about this with the Quantum Computing Association, with the heads of Cyber Command. I believe there is merit in this technology. I believe Canada and our US partners should be investing significantly in it because the practical applications, especially in the Arctic, as it relates to sovereign state defense, it has practical, safe defense applications. This is not something that we'd be using for aggression. This would be something for protecting sovereign state, using the technology to enhance the existing system that's now being decommissioned. So, I was just curious. You know, you've done a lot of work in the microgravity experimentation here, terrestrial based. You're ramping the results. I was very curious what your proposed next steps are.
So again, I'm not proposing all this work. It's different group.
Yes.
And I know that different group that they are planning, but I mean, it's again, people plan very ambitiously. So
Mhm.
they are planning like maybe a couple of years later, we can make it a space demonstration. So, but we also know that sometimes there's a lot of technical challenges. So we don't really know that it can be really fast, or maybe they can demonstrate or not. So it will be all depend on the how technology can progress. But I agree that there are importance on this one, and there's a lot of interesting thing to study. And NIST and also DoD, especially Army, I know that they are working on this one a lot.
I know the guys at NIST because I sit on the Electricity Safety Council, and I wrote
Okay.
the cybersecurity framework in conjunction with NIST. So I hear
Okay.
what you're saying. A lot of folks are really closely examining the research being conducted here, folks, and I
Yeah.
congratulate you on your breakthroughs. I'm just curious what kind of time frame. They keep giving me a 3 to 5 year span for quantum computing. I know XLR and CLR are still early stages, but with the quantum radar, I see that being coming to production a little earlier than the other technology because the practical applications are needed.
I agree, but I don't really know very much, but my just limiting my knowledge, my
Understood.
concern is the sensitivity. Can
Absolutely.
it really do better than the classical radar right now?
Uh-huh.
So I think that have to be answered, and there's a many idea to break that sensitivity, and also can you really compare with the normal antenna, which we have a perfect like great system already. It's like really comparable with this new way, but maybe there's just some kind of breakthrough and some kind of some easy way to break through to make it better, more sensitive and small and everything. But still, there is some of the question, important question need to be answered, and I think that's kind of dragging a little bit down. That's my guess.
My hope is to clear the decks, and you're right. I think there are answers that need to be addressed, and there is not only the micro sensitivity, but there's the security sensitivity here. So I'm going to take this one offline. I've reached out to you on LinkedIn.
Okay.
Happy to have the conversation, but yeah, no, I'd taken my eye off on quantum for the last 2.5 years. I have to say, there's been so many breakthroughs. I'm just playing catch up. So I do apologize. I don't have the domain knowledge that you do, and I appreciate the time and in your day presenting this information. I really do appreciate that.
Thank you for the joining.
Thank you, Doctor.
All right, there's another question from Nicholas. For the quantum radar, what are ways to distinguish an unlikely signal from a higher frequency, a more likely signal from a lower frequency signal?
When you say frequencies, what kind of frequency are we talking about? Like, are we talking about the different carrier frequency? Like when you tune the radio, like AM radio, we can change the different frequency, or are you talking about this modulation frequency from the carrier?
Hi, that was my question, Nick Gorgone. Yeah, if you go back to the image of the quantum radar, when you started to see that wave peak spread with the higher frequencies. Oh, you passed it actually. It was
This one is
after the next slide, I think.
this one.
Yes. When you start to see that one peak split into multiple peaks.
Yes.
For instance, if you're reading this off, and you measure something, for instance, it's like +5 megahertz, that could be the very tail of the black frequency, where you would say the radio frequency is off, but it also could be quite near the peak, the right peak of the blue frequency. Is there a way to distinguish whether it's a very unlikely radio off, or if you've sensed something that's radio on? Is it just doing like multiple measurements of the same signal to try and average that out, or other methods?
So sorry, can you rephrase the question? It's very technical, so it's hard to follow without any like.
Sorry, yeah, and maybe it's completely wrong because I'm not a specialist in this, but for instance, this plot makes it look like you could read different probabilities of seeing some frequency depending on what radio signal is coming at your detector.
Sure.
Is that right? Am I reading that right, first of all?
I think that's correct. So what's happening here is that when there's no RF signal, so no sound is going in there, you will see the black line that just nothing is splitted. But when you have like maybe one frequency coming in to this radio signal, then you start seeing the splitting by the amount of frequency.
Okay, so you would see a readout in a detector that would be like this double peak sort of.
Yes.
Oh, okay. I think that answers my question, and thank you.
Okay, great.
Okay, thank you. I can see there is a comment from Ron that one of Dr. Kim's slides showed a sensor in a glass tube. This might be the source for a new type of phased array radar tech. So this is the last comment.
Okay.
All right. Yeah, do we have more questions or comments?
Thank you for great questions. Like
Yes,
a lot of things that I never think about it. So
very interesting discussion. So also thanks for answering all the questions. All right, so I think we can conclude. So maybe I'll now stop sharing the slides as well. So Dr. Kim, thank you once again for this great presentation and also answering all the questions. So we really learned a lot and enjoyed this talk. So we would also like to thank all the participants. I'll now stop sharing the slides. And yeah, we invite all of you to attend our next meetups in June and July. So hope to see you next time.
thank you again, everyone. Happy holiday.
Thank you.
Thank you.
Thank you.